All right. Let's start off with homework questions, because we got the exam looming. Homework is kind of on a tight schedule. Any questions? What do we got? Backouts.
About the fourth problem, do we have to just write out each single variable, or we have to use any equations or expressions there to support?
No, I'm looking for equations are going to be straightforward to come up with for different systems. So those are not going to have the same equation for different systems. So these are all the stat mech terms. So I want you to give me an intuitive understanding of what these terms actually mean. Mathematically, we're going to hammer those in pretty aggressively, and it's going to change from you have monatomic gas versus diatomic gas. So all of those are going to be completely different given the system. So I want you to give me a physical intuition of what these terms mean, so that when you read the book, you can actually be like, oh, okay, that's what they're talking about. So one thing that I try and do, and I'm not very good at it, especially when it gets really in the depth of the derivations, is I'm trying to force myself, whenever I write a variable, not to be like, mu or gamma, to actually like refer to the term with its specific term, and to differentiate between the symbol we use to represent a variable and then actually state what that variable is. And so this is an attempt to get you to think like that as well. So that when you see the equation itself is it's interaction between fundamental variables, not just an abstract term. Yes, question?
Yeah, my question was on 1D, where you ask about finding a temperature at which the mixture will phase separate.
Yes.
Are you looking for something like an upper consulate temperature, like in homework 5, or is that just the term that applies to all?
In this case, yes. This is a fairly simple system, so in a simple system, you would expect that at higher temperatures, things will be more miscible. If you have a more complex system where there's a significant entropic contribution, as in the case of polymers, then you would have potentially an upper and a lower consulate temperature. In this case here, no, it would be potentially an upper consulate, but word to the wise, it's kind of a trick question. So the main reason is I want you to come up with rationale for why there may or may not be a phase transition. Right, so what I'm looking for is a really fundamental discussion of how would we ever know, based on the free energy profile, what would a phase transition look like? How would we know? Does anyone have an idea that we can use as a hint? Use it as a topic of discussion. So if we were to draw out a profile of the Gibbs free energy as a function of x of one of the components, what would it look like if they were fully miscible?
It would be like an ideal mixture, right?
What would that look like?
It'd be negative.
Be negative the whole time, right? That would be a fully miscible system. Now, what would be an immiscible system?
It would be positive.
Right, so in the middle, of course, it would be positive. It doesn't necessarily actually have to be positive, right? Over here, it's always going to be negative because of the entropic contribution. So in this situation here, right, this is going to be a two-phase system. Right, the system doesn't have to have, the free energy doesn't have to be, the free energy doesn't have to be rather higher than the individual sort of linear combination contributions, right? There just has to be an accessible state that is lower than a state that is near it. Does that make sense? So in this case here, this is obviously going to be a two-phase system because this has more free energy, right? So it's almost completely inaccessible from an adiabatic system, right? You'd have to add or subtract heat. You could never get to the state from an adiabatic process. You could also have a system potentially that looked like this as well. That would be a two-phase system also. Because if I try to create a mixture here, then in the vicinity of this state, there are additional states that have a lower free energy. And what's characteristic about the systems that have a two-phase split? What's characteristic about them?
They have a minimum in the Gibbs free energy.
They have a minimum, but they also have what? Slope. What kind of
Inflection
slope?
points.
They have inflection points. Right, so this case here, this is stable, this is unstable, oops. And this is stable here. So if you ever have an inflection point where you form an unstable fluid, then you know you're going to have a two-phase separation. Any more questions on the homework? So I think this homework is a very, very important one for the exam, because the questions are significantly more open-ended, and they test fundamental concepts that we've covered throughout the course. So in the case of the energy balance, right, if it's an ideal mixture, we can sort of treat the enthalpy of fluid A and the enthalpy of fluid B, and the enthalpy of fluid A in, enthalpy out, right? But in the case of a non-ideal mixture, we no longer can do that. So our reference states that we select have to vary based on what's the temperature and pressure in the phase of the reference state. We'll have to be able to be comfortable mixing and demixing in order to calculate the enthalpies. Right? So these are some key concepts. And this one here is another fundamental key concept that we're testing, or that I may be testing on the exam, I should say. Any more questions? All right. Let's move on to more stat mech. So I will not be holding office hours tomorrow, but the homework is due Wednesday afternoon, so any last minute questions can be resolved in class on Wednesday. I'll have office hours on Tuesday for some final kind of study help questions.
Thursday.
Office hours Thursday, yes. Yeah, so exam prep type questions. Okay, so last lecture, we're going to continue on with the ideal monatomic gas. But this time we're going to calculate basically all the properties. Excuse me. So what we did is we calculated the partition function for a collection of ideal monatomic gas particles. The canonical partition function, which we denote by Q, and there's additional partition functions that we'll talk about in the near future. This is NV beta, right? The canonical partition function is analogous to the Helmholtz energy. Now, we're not going through the Helmholtz energy to kind of draw connections between the microscopic world and the macroscopic world, because Helmholtz isn't something that I can just sort of think about and hold in my hand very nicely, right? Internal energy, pressure, these are things that are much more physically intuitive for us to understand. So instead of us going from the Helmholtz, from the canonical directly to the Helmholtz, we'll get there eventually, but I think it's more intuitive to think about in terms of energy and pressure and things like that. For a collection of particles that are indistinguishable, we can write the canonical partition function for a collection of particles as the partition function for a single particle, raised to the number and corrected for by an indistinguishability factor. So this expression here is for a collection of non-interacting indistinguishable particles. Interacting and indistinguishable. I'm just going to abbreviate it because it's it's a huge word. The partition function we considered was just the translational contribution and this has contributions from translations in the X, Y, and Z direction. This is based on particle in a box. It's symmetric. So this is the equivalent of just the partition function in the X direction cubed. And if we substitute it in, this is a function of the quantum number Lx. Now the partition function for the canonical ensemble is just a Boltzmann scaled energy of the system. Now the Maxwell-Boltzmann distribution is just E raised to the minus beta of the energy. So in this case here, here we have the minus beta, and then the energy right? So we're scaling based on effectively the higher the temperature, the less important the energy becomes. Right? At infinite temperature, all states are equally probable. Otherwise, we would be violating the second law of thermodynamics. In this contribution here, this is the energy of a particle in a box as a function of an integer quantum number here. And we're summing up over all the possible conditions. We approximated this, a good approximation, but an approximation nonetheless, as a continuous distribution. dlx cubed. And this big, complicated, infinite summation or infinite integral or unbounded integral actually spits out a relatively simple expression. And so the partition function, which is kind of a little bit confusing, we're saying that it's basically the summation of all possible energy states, but it actually just spits out a number. So if I were to plug in the mass of a particular single atom, Planck's constant, the volume that it occupies, the partition function, which is the summation of all the states scaled by the temperature, is just a number. That's it. So it starts off being this seemingly unmanageable function, but in the end, it's just a relatively simple, direct explicit function. That's just a number. The number itself isn't particularly meaningful. What is meaningful is how that number changes with respect to other properties. How does the number of states change as I increase the temperature? How does the number of states change if I increase the number of particles? How does the number of states change if I change the volume? That's where all the interesting information is, right? So you can kind of think of this here like the enthalpy. The enthalpy of a fluid doesn't really matter. All that really matters is how does it change as I mix it with something else? How does it change when I change its pressure? Because that's how I'm interacting with the real world, right? It doesn't matter to me that I could add or subtract energy from an atom by taking or giving away electrons. For the most part, when I'm boiling a pot of water, I'm not adding or subtracting electrons, right? So I only care about how I'm interacting with the system. But truth be told, there's energy stored in that in the electronic states. There's energy stored in how many protons and neutrons there are. There's energy stored in how the quarks are assembled in those protons and neutrons, right? So all that information is interesting, and it kind of is analogous here to the partition function where, yeah, we could calculate all of it, but we don't really care that much about the total number. We just care how it changes when I interact with the system. And then from here, we calculated several properties. The internal energy is the one that we started with, and we're going to expand on that today. From previous discussions, this is equal to the negative natural log of the partition function with respect to changes in the temperature of the system, or beta, which is sort of the scaled temperature from a statistical perspective. And when we applied this relationship here for the internal energy of the system, what we got was our expected outcome, 3/2 n over beta, which we can replace with three halves times the number of moles times the Boltzmann constant temperature. So if you plug in Avogadro's number, n times the Boltzmann constant is the gas constant. So that's our connection between the microscopic and the macroscopic world. Now, what our goal is for today is we're going to relate the canonical partition function, which we can derive for an ideal monatomic gas, and then it's going to get more complicated as we have more complicated molecules. For example, we could have a diatomic gas, we could have a multiatomic gas with lots of additional degrees of freedom, and then we can also introduce interactions between the particles where this part right here will fall apart. Right? The partition function for a collection of particles that interact is not as simple as just taking the number of configurations for particle 1 times it by particle 2 times it by particle 3 times it by particle 4. Right? That's all we're doing right here. This expression here is we have our indistinguishability factor times by Q1 times by Q2 times by Q3. Right? So if all these particles are identical, 1, 2, 3, 4, 5, 6, all the way to n, it just, the partition function raised to the n power, and then normalizing it by the fact that we don't know which one's particle 1, which one's particle 2, which one's particle 3. So this part right here, this assumption will break down when we get to more complicated systems. If we change how an individual particle behaves, then the single particle partition function will break down. So switching from a monatomic to a diatomic to a multivalent, or to a multiatomic gas particle, that'll change things as well. Okay, so what we're going to do is we're going to cheat a little bit, and we're going to rely very heavily on classical thermodynamics. So I would not quantify this or classify this as an exceptionally rigorous approach, but this is effectively the approach that the Sandler book takes, and I think it's plenty good enough to give us the concept of how we draw connections between the macroscopic and the microscopic world. So what we're first going to do is we're going to get rid of this unit beta for a little time being to sort of get us a little bit closer to what we have seen classically before. Right, and we're going to use the internal energy as our gateway into the macroscopic world. So we can replace this just by doing a substitution of variables, noting that so if we then calculate, let's see if I can get this right, -1R. So substituting the variables out, we can rewrite the internal energy as a function of temperature. This is going to be all too familiar. We're going to expand the natural log of the partition function with respect to temperature and volume. Exactly like what we've done for classical. I'll drop the n, I'll just have the v. And then from here on out, it's going to be a little bit of manipulation to get it into a form that we can start to compare to something that we're used to macroscopically. Right, so then all we're going to be doing now is just manipulating this again and again and again until it looks like something that we've derived from classical thermo. In other words, we're trying to get this to look like some form of the combined first and second law of thermodynamics. Then the same way that we developed Maxwell relations and thermodynamic identities, hopefully we can develop identities relating between stat mech and classical thermo. So if we multiply both sides by this expression here, k over t, or kt squared, then we can kind of get it to look a little bit more similar. All right, so if I times dlnq dt by kbt squared, that's actually just U, the internal energy, the expression we just derived. And then this one doesn't simplify down quite yet. Okay, a few other manipulations. Another variable transformation. The objective here, we're getting it out of dt space and putting it into du space. Again, this is one of these derivations where we know the outcome, so it's sort of like it's a wandering path to get there. So we're going to take this expression, substitute it into here. And we're almost there. So we're going to combine these two terms together. So basically take all the differential stuff and slap them together and substitute in our internal energy from the partition function expression. So I skipped over a little bit of the arithmetic, but it should all just basically be an algebraic substitution. It's a little bit tricky because you have so many sort of temperatures and Boltzmanns on the top and bottom, but as long as I didn't make a mistake transcribing my notes, I think it should be good. Okay, so this may not look like much, but it looks very similar to what we have for the combined first and second law. So we have a T ds. I mean, there's a Boltzmann constant here, but we can very easily take care of that. That's just a constant. So then we would expect that this expression inside of here should be somewhat related to the entropy. In fact, it is the entropy. And likewise over here, we've got a dV term and a minus pressure term. So by comparing these two expressions, and noting that we trust the combined first and second law that we derived from classical thermodynamics, we didn't make any assumptions, we didn't violate any rules. In all of this derivation, what we did is we've treated everything as a potential variable except for the Boltzmann constant, right? So everything is a function of everything else. So when we compare the derivative of u over t, we're considering the fact that both u is a function of t and t is a function of u. Right, so we made no assumptions whatsoever. It's just strictly algebra and calculus from this point onwards. So from here, we can derive additional relationships from the partition function. The pressure is related to how the partition function changes as I restrict the volume of a particle, which makes pretty intuitive sense. Right? If I shrink the volume that the box has contained in, right, that should be somehow manifested in the pressure, just the same way that if I shrink the volume of a macroscopic system, the pressure increases as well. The entropy is a bit more complicated. So it turns out the canonical partition function is not the cleanest way to visualize the entropy, but we can talk a little bit about it. The Helmholtz energy, as we know, is defined as U minus Ts, the internal energy minus the temperature, times by the entropy. We can go through the math, but actually, as it turns out, it turns to be a very, very simple expression. Effectively, everything just cancels out nicely. So the Helmholtz energy is the most directly related to the canonical partition function. And that should make intuitive sense because we're holding constant exactly the same variables that the Helmholtz naturally wants to be working in. Number of particles, temperature, and volume. Gibbs free energy is the number of particles, temperature, and pressure. So there will also be an ensemble that the Gibbs free energy is the most directly related to. So this also makes pretty good intuitive sense as well, because if we look at dA dV at constant T, this gives us pressure. Right, from classical thermo. This is how one of the ways we can also know what the native variables are for each of these different thermodynamic functions, is if the first derivative gives us another thermodynamic function. That's how we derive all of our identities and maximum relations. And same thing, if you take the partial derivative of Helmholtz with respect to temperature, it gives us the entropy. So every statistical mechanic ensemble has a thermodynamic variable that is directly related to it. The mathematics is just a little bit tricky and a little bit more on the abstract side of things. So we can continue on from here. We can have an expression for the chemical potential, which may be important for phase behavior calculations. Now in the Helmholtz, using Helmholtz energy, this is the change in Helmholtz as you change the number of moles of particle I while holding temperature, volume, and all the other compounds constant, so Nj not equal to I. So we can carry this on directly to the statistical world. And we have more expressions from thermodynamics. And we can continue on basically, but from this point onwards, we'll just be combining other expressions. So if we wanted the enthalpy, right, we could just grab U, which is, we have written over here. Where do I have it here? Grab the U, grab the P, grab the V, and then we can derive a whole new expression right there. So instead of just me hammering them out. But from this point onwards, we could just manipulate all of these expressions through classical thermodynamic expressions without having to rely too much on the statistical world as well. Okay, any questions? So we cheated the best we could to get us to an end result. So now let's go back through and recalculate some of these expressions for the ideal monatomic gas. So we can see how does the particle in a box manifest itself for all the other macroscopic thermodynamic properties. So as a recap, talked a little bit about it here, but at this point we only focused on the translational. Let's just consider the other possible ways that a molecule can store energy and then say why we're neglecting them. So we're going to go back and do it a little bit more rigorously. So if we look at the energy of a particular gas particle for a monatomic, so there's no rotations, no vibrations, or anything like that. What we considered was the energy associated with the translation. We could potentially have energy associated with the electrons or the electronic energy states. This would be something that could be activated if you excite it using UV light. And there's also energy stored in the states of the nucleus itself. Right? The nucleus can have elevated and elevated energy states as well. So if we were to then write the partition function for a single monatomic gas particle, in this case considering all three of these different possible energy states, right? The partition function is just a Boltzmann factor scaling the energy of every individual state. So if a monatomic gas particle is zipping along, it can also have a particular electronic state, it can also have a particular nuclear state. So in this case, it would be the summation over all states scaled the translational state, the electronic, and the nuclear. Using exponent properties, right? If I'm adding together elements inside of the exponent, that's the same thing as multiplying them outside. So then we can very straightforward rewrite this as by assuming that their energy is not correlated. Mathematically, how I know that the energy is not correlated is if I have expressions for the energy of the translation of a particle. If it has no terms and expressions related to the electronic energy state, or no terms or expressions related to the nuclear energy state, that means if I change this energy or this one, it doesn't affect this energy here. So physically, that's saying that how the electrons are interacting or moving around inside of a particle doesn't affect how much it's zipping along. Now, there may be scenarios where that's not the case, right? But in the case of an ideal monatomic gas where there are no interactions, it makes pretty good intuitive sense, right? It's kind of like jumping up and down on a cruise ship, right? It doesn't impact how the direction of the ship is going. So intuitively, that's what it means. And then mathematically, that allows us to split them into the individual partition functions. So that means we can derive a theory for a stationary gas particle playing around with its energy levels electronically, and then also playing around with the energy levels in the nucleus, which is another heavily quantum mechanical area. So if we assume, and again, this is a good assumption, right? In the absence of an expression for how we handle the electronic and nuclear states, that the energy of the electronic state is much, much greater than the energy of translation, and the energy of the nuclear states is much, much greater than the energy of the translation. What that allows us to do is simplify our calculations. This is all stuff that we did already, but we didn't go over into the details too much. So that would mean that E So if the energy of an electronic transition is really, really big, which in this case it actually is, right? It's actually on the order of several thousand degrees Kelvin. So you don't actually really have to consider these transitions until you get to very high energies. So unless you have very high temperatures, the probability in it being an excited electronic energy state is very, very low, meaning that this basically is an exponential decay that gets close to 0. E to the 0 is just equal to 1. Same thing would happen for the nuclear states. In which case we can approximate the partition function excuse me. We can approximate the partition function as only the contributions from the translational modes. So, one quick discussion, a little side note. The heat capacity as a function of temperature. How do we think it should look? So, at low temperatures, do you think we should have a high or a low heat capacity? I had a couple highs, a couple of lows.
Lower temperatures, lower.
Why is that? What's the intuitive reason for that?
Lower, fewer states available.
Right, so the internal energy, backwards. The heat capacity is defined based on how the internal energy changes with respect to temperature. So let's say I have 1 joule's worth of energy to give a mole's worth of particles. Would I expect the temperature to increase a lot or a little bit at low versus high temperatures? Right, so I have 1 joule's worth of energy, and I'm going to give it to a mole's worth of gas particles. At low temperatures, there's not that many ways where it can store that energy, right? So what it has to do is the gas particles have to raise their energy to give them the opportunity to store that joule's worth of energy in more and more different ways. So what's effectively going to happen is that it's going to start off very high. So a little amount of energy, right, is going to manifest itself in a relatively larger temperature change. As we continue to increase, the heat capacity will asymptotically approach a final value. Now this is the final value here, where basically all of the energy modes of the particle have been activated. So in the case of something a little bit more complex, let's say like a diatomic gas particle. A diatomic gas particle is going to have translations, it's going to have rotations, it's also going to have vibrations, right? The last of those to be activated is going to be vibrations. Further, if you keep on increasing it, then you're actually going to start activating the electronic energy states as well. For the most part, that's not going to be a fairly probable scenario that we're going to deal with, unless you start looking at very high temperatures like you might experience in a furnace, for example, for a power plant. Okay, so that's a little bit more of a discussion on sort of a physical intuition of how we got to where we got to. I shouldn't have erased these. Keep us here. This is S and this is P. Okay, so let's box this off a little bit. Our partition function that we derived previously, we're just going to go through and crunch the numbers. Okay, so this is the canonical partition function. This is assuming that they're non-interacting particles, meaning that there is no configurations of the system that have different energies based on the orientation of the particles. Now, the virial equation of state has an additional contribution to the energy based on the orientation of the particles. We're also going to have a partition function that's associated with the configuration. And that's where we're going to have interacting systems where things get very, very much more complicated. But in this case here, we're going to say it's a collection of identical particles that are indistinguishable, that are non-interacting. So that allows us, and we're also assuming that the number of energy states is much, much greater than the number of particles. such that we can neglect the fact that two particles might be existing in exactly the same energy state. So those are all the assumptions that went into this little simple expression right here. What we derived previously is that it looks like this. In this case here, it's a function of temperature as opposed to beta. And for all of our calculations here, the natural log of the partition function is going to be the variable that we care about the most. So I'll just go ahead and write that down right away. Okay. So each of these terms are going to contribute to different thermodynamic functions. We've already done internal energy. The only one of these expressions here, I think I've, no, I haven't erased them here. Right, the only one of these expressions that have any dependence on temperature is this middle one right here. So it's the only one that's going to matter, and we've done this one already. So the internal energy, in this case here, we apply this expression and we spit out we can calculate the heat capacity. The pressure. What result are we hoping to get here? What law are we hoping to get out from classical thermo?
Ideal gas.
That's our goal. We're going to hope it's the ideal gas law. Okay, so the pressure tells us how does the natural log of the partition function vary as I vary the volume of the box that these particles are contained within. So this first expression here, no volume. This second expression here, no volume. It's only going to be this third expression right here. So in this case, we're looking at, it's going to be kBT times by d dV of n ln of v. Right? The number of moles in the system is not a function of the volume. kBTN d ln v dV. This is going to be equal to n kBT over V. Or in other ways, we can write this as P equals and we have the ideal gas law. That comes very naturally straight out of this interaction. So if we combine right now, n is per particle. If we rewrite n as number of moles, then we would have to change the Boltzmann constant to the ideal gas constant. And this is where things get a little bit tricky relating between classical and statistical thermodynamics. Again, oftentimes when you're working through these problems, even if you give it an explicit expression, it's not crystal clear. Do I times by NA? Do I divide by NA? And so oftentimes you'll find yourself getting wildly, massively wrong numbers off by, 10 to the minus 40, 10 to the 40, because it's not always perfectly clear, right? Is n per mole or is n per particle? But in StatMech, the assumption is that everything is per particle. So unless you actively convert from particles to moles, everything you do is per particle. Right? So if you're asked what is the internal energy of a mole or 2 moles worth, then it's going to be 2 times 6.022 times 10 to the 23. Okay. I'm actually going to have to kill something. Are we going to do S? Oh, yeah, we do S. Okay, so we did pressure. I'm going to delete this one here. So the next one, let's do the Helmholtz energy. Helmholtz allows us to introduce a very common approximation that's being used. So the Helmholtz, I'll just rewrite it. So instead of putting in all this stuff right here, I should write it as a function of the single particle partition function. This is going to be the expression for the Helmholtz energy. So if we expand this, we run into a problem. How many of you have played on your calculators and that when you discovered the factorial button, you go, oh, 2 factorial, 3 factorial, 4 factorial, and as soon as you get to a relatively modest number, it just blows up, and it's too large to even handle. So now we have an issue. How do we evaluate the factorial of 10 to the 23? That's something that I'm sure nobody's calculator can handle. So what we do in StatMech very commonly is we employ something called Stirling's approximation. In this case, we write that the natural log of a factorial can be approximated, and once n gets anything reasonable, like over 10, 20, this is a very good approximation. Right? So it's not so great when you have like 4 particles or 5 particles, in which case you can just directly calculate that. Right? But anytime you get any sort of significant number, in the tens, this approximation becomes quite good. We can rewrite this as the number of particles times the natural log of particles minus the number of particles. We could also write this as well, noting the natural log of E is just 1. That allows us to sort of combine these expressions together a little bit. So that allows us then to write actually an explicit expression for the Helmholtz energy. The partition function. And 2 more to tie us up. The entropy. Again, we're going to cheat. We're going to use actually our classical Thermo terms right here. We're going to say that the Helmholtz is equal to the entropy is equal to minus the rate of change of the Helmholtz with respect to temperature, holding the volume constant, well, N and V constant rather. This 5/2 comes from the temperature dependence of the single particle partition function, which is 1 over 1 plus 3/2. So 2 over 2 plus 3 over 2 is 5 over 2. That's where that little thing comes from there. And then lastly, the chemical potential. We have an expression for that there. So a lot of these expressions, we're not unfortunately going to have the time to hammer away with too much. We're going to focus a little bit more on energy, enthalpy, pressure, things like that. But effectively, if we were to apply statistical mechanics to help us solve, let's say, the type of problem that we're working on right now for the exam 2, phase equilibrium behavior, the chemical potential is effectively the way that we would use to calculate what the partial fugacity is. Right? That's how those two would be related. So the challenge, though, is that this is only one half of the equation. So if you're asked to calculate the chemical potential of an ideal monatomic gas, well, we have that expression right here. It's not going to be extremely useful, especially because if we're trying to do liquid vapor equilibrium for an ideal monatomic gas, you basically have to do cryo experiments, right? I don't know what the melting or sorry, the boiling temperature of argon or something like that is, but for helium and neon, it's extremely low. You're talking single digits or tens of kelvins. But so that's one of the reasons why when you first start reading about stat mech and you go back and you look through all of these classic physics papers talking about how does liquid helium behave? How does cryo helium or cryo argon behave? And the idea behind all these experiments that were done kind of in the 60s and 70s, right? That's when the experimental capabilities of national labs or university labs or research facilities were actually good enough that they could actually begin to test some of these statistical mechanical theories. So when you go back through, and if you ever run across any of these papers from the 50s, 60s, and 70s doing cryo experiments, you might say, why is everyone wasting their time, right? Nobody's using these fluids for anything on a large-scale commercial process other than I guess MRI machines use liquid helium, but the commercial scale production of these things is relatively small. But the whole point of going through and doing those fundamental physics experiments is to validate and say, where do these approximations go wrong? Right? We actually had to throw in a relatively large number of approximations to get this expression right here. Right? Non-interacting, we're assuming that the energy modes are independent. How can we develop a system to test, is it independent? Are there conditions where the electronic state is actually correlated to the translational modes? Are the rotational modes correlated to the density of the fluid? These are some of the questions that can be answered by doing really small scale fundamental type studies. It seems like it might be a waste of time coming from an engineering perspective, but there is certainly merit to it. I'm just glad that physicists take care of it. I don't have to take care of it, right? I'll appreciate what they've learned from it, but that's a lifetime of work just to study a few small key assumptions in these expressions here. So the most part, what I'm trying to accomplish with the stat mech portion of the class is to at least give everyone a physical intuition for kind of the questions that we're still struggling with, not to take assumptions for granted, and also to be able to translate when we do see these fundamental molecular type level papers. Don't just sort of immediately dismiss them, or at least you'll have somewhat of a scrutinizing eye to say, aha, I know what these assumptions mean, or I know what the partition function is. Those types of things are really kind of critically important for moving forward in research. All right, exam review on Wednesday, exam on Friday, same rules apply. You'll get a cheat sheet, 1 page front and back. The content on the exam is going to be open to everything we've covered in the class, obviously with a very, very strong emphasis on fluid phase equilibrium. But as you can see from this week's homework, don't forget that we've still done energy balances and entropy balances, right? And that the energy and entropy of a system, right, of a mixture can't be separated. So the energy balance is exactly the same, right? The same energy that flows in is the same energy that flows out for a steady state process, but I can no longer break it down to A flowing in and B flowing in and A flowing out and B flowing out. It's the mixed fluid flowing in and the mixed fluid flowing out, right? So you have to consider mixing and unmixing for your reference state conditions, right? So that's kind of the main thing to consider from the previous type stuff. All right, see ya.